Hello and welcome to the lecture LSTM. In this lecture, we are first try to understand what are the problems of RNN, namely vanishing gradient problem and long-term contextual dependency issue. Then we introduce LSTM to mitigate this problem. Then we discuss the LSTM architecture and then we try to understand how LSTM solves vanishing gradient problem. In the last lecture, we have discussed the basic RNN architecture for sequential modeling. Now, what we have seen that this is a basic structure of the recurrent neural network, and this is the say kind of short description of the network. If we unfold this network with respect to different time steps, it is look like this. That means, let's say there is a t times instance or t plus 1 time instance. So S0 is the first state, X0 is the input, Y0 is the output, and for the next step S1, there is a H0, that is hidden state, which has been calculated here, is going to the next state of the RNN. So this time instance 1, this X1 is the present input, H0 is the input from the last state, and Y1 is the output. Now there is a shared weight of all these RNN nodes, Wx for input, present input, Wh for the previous state input, and Wo for the output. And these are basically same for all the nodes. In final nodes, it's St minus 1. So this Ht minus 1 is calculated here, which is finally come here, last state St, and similar Xt is coming, Ht minus 1 for here, and we get the Yt, and ultimately we get the Ht. Now what do you mean by Ht? Ht of in this every state, this equation or this function has been carried out. F of W, W is basically for weight function. H of T1, it is coming from the previous state. Xt, this is the present state input, and if we just describe or represent in this mathematical formula, that Ht is equal to tan of H. Tan H is basically the nonlinearity. Wh is this function into Ht1 minus 1, so this, and plus Wx, this function, and Xt, this function. So Wx is this weight matrix, is present input. So what we find that this Ht, and these or this, you can put any values from 1 to t, here we can get this equation. And what about Yt? In every step, that's Wo into H of t. H of t, so for t is equal to 1 to small t, this is the number of time steps, the time steps. So this is the basic idea of the RNN architecture. Now the question is that we just remind or recollect the fact why it is sequential in nature. You see, in spatial models, there is this, if you consider only one node, it's a kind of spatial model. If we know this thing, there is no, but in RNN, there is a x1, in that it is present input, as well as there is input from the previous state. So what we have to understand that this state, when calculating this state, there is some influence or some contribution from the previous state. Just for example, if it is a sentence, now this, when we consider this word or we model this word, there is some relation or some influence from the previous word. That is important to understand. So in this way, this S2, now S0, S1, this S1 is what, or H1 is what? It is basically this influence from S0, S1 that is in H1. It is coming from the previous step and it is going to influence S2. So there is a temporal relationship or temporal input is coming along with this the present input. And this sequentiality or this temporal relation, it is not present in the spatial model like CNN. In RNN, this is the major difference that we have to understand. So somehow there is a in different time sequence this, and why particularly these things are useful in ordered sequence or a sequence in just for a sentence, because this a word in a sentence is depend or is depending on the previous word or other words of the sentence, and this context or this relationship, its temporal relationship, is being modeled by this RNN. So that in that way, the RNN, although it's a very naive structure, very simplistic structure, these things is being modeled. This sequential or temporal relationship is modeled by virtue of this RNN architecture. Now, in this class, we are trying to understand what are the problems with basic RNN. Okay. So the first problem is vanishing gradient. Let's try to understand the major limitation of recurrent neural network occurrence is the vanishing gradient. Why it very major problem? This occurs during the backpropagation time that we have discussed PPT in the last class. Now, as we understand that what is BPGT, that in BPGT the gradients are propagated backwards direction across the multiple time steps. Now you see, when gradient is calculated for, let's say for this calculating WH, so every steps these WHs are being, this is the weight parameter, so it should be modified as per the error gradients and the training time, that is the normal backpropagation. So backpropagation through time, this is coming from here because this is the final, and this error is basically propagated. This error will come here and this is propagated. This coming from here, propagated in this way. So it is when it is propagated in backward direction at every node from here to here, here to here, here to here, and so on. There is a, using the chain rule, we are calculating the error gradient the previous layer. So what it basically we do that the propagated backward across multiple, they are repeatedly multiplied by recurrent weights and activation function derivatives. That is we understood in the last class also. So this repeated multiplication of recurrent weights and activation function means what? What we have seen that this weight, basically this error gradient at the and this activation function derivative both are less than 1 in if we use the gradient descent method. So definitely what happens if multiple steps are used, this gradient become very close to 0, and is decaying almost equal to 0. So it kills the gradient, and that is the basic problem, as the gradient is basically vanishing or decaying. That's why it's called vanishing gradient. So when these values are less than 1, what we have said just now, the gradient magnitude decreases exponentially, causing the gradients associated with the earlier time step to become extremely small or approach to 0. So this is the major issue. Consequently, the corresponding weight updates become ineffective. Definitely. So if gradient become very less, what happens? This in this initial layers, the gradient value is very close to 0. So this weight updation become very smaller, almost negligible. So for these layers, the training procedure is basically stopped or hugely slow. So that is the basic issue. Weight updates become ineffective, making it difficult for network to learn information from the distance steps. So this is the basic problem of a simple RNA, and this is basically due to vanishing gradient problem. Now, what is the effect of this? Now, if this problem happened, this vanishing gradient problem, this caused a significant, a serious limitation, difficulty in learning long-term dependencies. Now, what does this mean? You see here, there is a word here, and there is a word here, and this t is bit high. Let's say 15, 20, something. Now, if the weight are decayed very much at here, so there is a very less effect of S1 toward S2. Or if there is a relation between these two are not properly, that relation becomes weakened. So that is basically being said. Difficulty learning long-term dependencies. Dependence is this relation. So difficulty, it makes difficult to learn long relation. So a simple RNN tends to give greater importance to the recent inputs while gradually losing information from earlier inputs. That is very easy to understand. Because what, again go back this figure. This since this is this time instance t minus 1, it is a long distance from h1. So it put more emphasis on h2 rather than this x1. That we want to say, thereby limiting this ability to capture relationship across the long sequences. So that is the meaning of this. Furthermore, RNN suffer from sequential computation because RNN is a sequential process. Since the hidden state at each time step depends on hidden state from the preceding steps. So what would be the problem for sequential computation? The computation cannot fully parallelized across the time steps, so leading to slower training and reduced CPU utilization, so particularly when processing long sequences. So this is another major issue from the computational point of view. So these are the major problems if we go for a very naive or a simple RNN structure. With this background, let us try to understand the vanishing gradient problem for BPTT algorithm, that means back propagation to time algorithm, in a bit in depth. So with the following equation, as we seen in our earlier lectures, the error gradient, we derived the error gradient with respect to WH. So from this. So what was the equation? Del of L of t. And what is L of t? Now this is a 4-node network. So this t is 1, 2, 3, 4. So this I is equal to 1 to t means this t is equal to 4. Okay. So that is the t. So del of LT of by del of WH, that we want to, because this is the error at this time step, and this is the this H in a particular this kind. This H is this. So what we are going to find out, what is the error gradient here. Let's say we try this. Now from where we have shown in the last lecture how. For just recapitulation, we try to understand that when you are calculating the error gradient here, one error gradient coming from here, and this others are coming through this and this. So basically it is the back propagation. So these two things, error gradient is coming using chain rule, and this is coming straight. So considering this equation is basically del of LT by del of HT, that the particular this HT is this particular error gradient what we are trying to understand. I is equal to 1 to T and del of HT by del of HI and del of HI into del of H. So this is the basic understanding of this. Now this thing del of HT by del of HI and I is equal to 1 to T, this particular thing. This is I and T, this I and T, this 2 and 4, let's say this is, or 1 and 4, this I and T may be a far apart. Let maybe T is equal to capital T and I is equal to 1, and T may be a long, this large number of 50. So what happened if this is the thing? This thing will happen that using this chain rule BPTT, it's shown that this WH of T is a diagonal matrix tan H derivative of this. So the gradient becomes a product of many matrices, since as per our assumption, I and T are far apart, I is equal to 1 and T is equal to 50. So this is the thing that we can show from the chain rule, and this dH of this dHT by dH1 I, that is very, if I and T are far apart, then this is multiplication, because this is a multiplication of many matrices. If the eigenvalues of the product are less than 1, the gradient is exponential. So that is the major reason of the vanishing gradient. Now tan h as sigmoid activation function, this derivative tan h of x is less than or equal to 1. Hence, for each multiplication, usually scales the gradient by a factor less than 1. So if you keep on multiply a gradient with less than 1 and many times, because many times means almost 50 or near 50. So what happened? So 0.9 becomes 0.00. It is very close to 0. So after many time step, gradient becomes almost 0. It is very close to 0. So the weights are initial times reducible negligible after. That is exactly what we have said in the previous slides. And this is the exact reason of the gradient is decaying or vanishing. So the weight updation stopped. And this is the known as the vanishing gradient problem. That is the actual reason. Mathematically, so. Okay. Now, this is the May-Valerian structure. That same thing, xt coming with wx, ht minus 1 coming with wh, this wx, this wh, and this is ht is formulated in this way, and then wo is 2 cats, wo is put it to sum of, you get the yt. So this is the May-Valerian structure. So what happened here? Now we consider this. this vanishing gradient problem, how complicated the problem issue. Now, just consider this a bit lengthy sentence. The kid playing football in the playground is very happy, and the kids playing football in the playground are happy. Now, you see, this is singular, so it's a is, it's a plural. So this sentence, these two words are far apart, but it is associated. So as this. So during backpropagation through time, BPT, gradients are multiplied repeatedly across time steps. So they shrink exponentially vanishing gradients. As a result, earlier time steps receive negligible weight updates and stop learning. So what happened that this influence of this to this become very almost we forget this. So it is become complicated to understand. It is or not. The simple RNN is not taking any prior precautions, is not suitable for learning or representing a long-term contextual dependencies in long sequence such as large sentence. This is exactly here. This is input, this is output. So that is this kind of dependency, because this kind of sentence is basically by this. So they fail to represent this long-term contextual dependency. That is the major problem of RNN. Now we have understood the problem of simple RNN, that is basically the vanishing gradient, and due to vanishing gradient, that is long distance context modeling is a problem for a simple or naive RNN. Now we are going to understand how another architecture, so improved architecture over RNN, that is called long short-term memory, that has been introduced in 1997 by Gautier et al. Now, long short-term memory, popularly known as LSTM, is an advanced type of RNA specifically designed to overcome the vanishing gradient problem and improve the learning of long-term dependencies. So LSTM is basically proposed to mitigate the problem of the simple or naive structure of the RNA. Now, what is the basic difference? Unlike this conventional RNA, LSTM uses memory cell and three main gates, namely forget gate, input gate, and output gate, to regulate the flow of information through the network. Okay? The forget gate determines which information should be discarded. The input gate controls which new information should be stored, and the output gate determines which information should be passed to the next state. So basically, this is the three major gates, and will come memory cell later. What do you mean memory cell? By virtue of this concept, LSTM is proposed to mitigate the problem of RNN, which is basically vanishing gradient, and for learning long-term dependencies. Now, most importantly, LSTM cell state provides relatively direct pathway of information and gradients to flow across the multiple time steps, reducing the exponential decay of gradients during backpropagation through time. That is a very important concept. Because apart from three gates that we have seen, that forget gate, input gate, and output gate, LSTM introduced another concept called cell state. This cell state provides a relatively direct pathway that we will see in our subsequent slides. that how this cell state provides this direct pathway for information and gradients to flow across the multiple steps. So information flows in the forward direction, a gradient is coming backward way for repetitive across multiple steps, reducing the exponential decay of gradients to the repetitive. And that if we can do this, definitely our vanishing gradient problem will be minimized. This enables LSTM to retain relevant information for longer periods and effectively learn long-term dependency in initial data. So, if we handle vanishing gradient, definitely it retains relevant information for longer periods, and this long-term dependency problem can be solved. Therefore, LSTM provides a more robust solution than simple RNNs for tasks involving long sequences, such as language modeling, speech recognition, machine translation, translation, etc. So this is the basic understanding of LSTM. Now come to the LSTM architecture. What LSTM architecture is basically said the cell state and three primary gates. The first of all, the forget gate is the forget gate determines which information from the previous cell state should be discarded. So information is coming in this way. This forget gate is basically this gate, and this xt is coming here. So we try to understand that what actually this is the sigma, this is the non-relative project, ft, and it is. So this ft is basically the forget gate. Next is the input gate. The input gate controls the amount of new information that should be stored in the cell state. And what is input gate? Input gate is basically that xt is coming, the new information. How much of this information stored in this node? So amount of new information that should be stored in the cell state. Okay. Next is the output gate. Output gate determines which portion of the updated cell state. So each of the cell state is exposed as the hidden state and passed to the next steps. So that it will basically actually what is the HT is. That will determine. We'll come details in this. Now, what is cell state? Cell state acts as a long-term memory pathway, allowing the relevant information to flow to the multiple time steps and reduce gradient. So this is the basically cell state part. So in multiple nodes, this cell state is basically, you see, there is the direct pathway. So that is the basic right to understand. So we'll come in details. Cell state. Okay. Now, first we start with forget gate that controls memory. The forget gate decides how much information from the previous cell state should be kept or forgotten. So this is basically coming from the previous state. It is coming here. So this forget gate helps the LSTM remove irrelevant or unnecessary information while keeping important information for the future steps. So that is basically it. So what is f of t? This sigma is a nonlinearity. Then wh of f of forget, wh of this, that is multiplied with ht minus 1, that is the information coming from the previous state, plus wx of f, so this xt plus star, and all our f is because of this gate. Now for a particular cell state, let's say ft is equal to 0, this ft is equal to 0 or near 0. The corresponding information in the previous cell state, ct minus 1, this nothing this, is erased or forgotten. If ft is equal to 0, 0 into this, so it is forgotten. Conversely, if ft is equal to 1 or near 1, the corresponding information ct minus is retained and passed unchanged to the next. And definitely we can understand if it is 1, so it is become ct minus. Okay, so this is the forget gate that they basically try to help information registered to be kept or forgotten. Okay, so this is the basic idea of forget get. Now come to the input get, that is selective writing. The input get determines what new information and how much of it should be written into the set state. Okay, so new information is coming by this state. While the forget get decide what information to remove, the input get decide what information to add. So this is for what to remove, now it is what to add. So how it is being computed? This IT is a sigma that WH of I was what is the input get, WH of this that this way plus WX, because this is WX and I for input get plus mass. So this is IT. Now what is the candidate cell state? That this IT is basically this CT, this tilde is tan H of WCH. So it is a candidate of HT1 plus WXC XT plus this. So this is the candidate to be added. Updating cell state, IT decide this IT, right, what component is to be updated, and CT bar or CT tilde provides the change components. And what is the updated cell state? This CT, that means this CT is basically f of t into CT minus 1 plus IT into CT. Here, ITCT represents the new candidate values scaled by how much to update each state value, and FT is to decide how much to remember the previous. So one thing is very important to understand here. This is two basic things. What new, how much new information is coming, and what amount of previous information retained. This is by forget get, this is by input get. And this CT basically, what is the cell state is basically by this. Forget get into CT means the previous information, IT input get means this candidate. So this is the basic idea of input get. Now about what is the output get, the controlled exposure. That output get determines how much information from the cell state is exposed as the hidden state at the current time state. So this is basically the sigma. This, although the cell state stores long-term memory, not all of it's needed at every time step. The output get selects the relevant information to pass. So what is the output? This sigma WH. This is output get or HT minus 1. So this is, and plus WX. This is also coming of OXT. So this is OT, and this we are going to find control exposure of this. The current cell state CT is first passed to the tan H, that this is tan H. So, so this is tan H, and activation function to scale the values minus 1 plus 1. The transformed cell state is then multiplied element wise with output get, that is OT, that is here, to produce the hidden state HT. HT is OT, the element wise multiplication of tan H of CT. So that is the way to get the state. So this is the way output get, that control that how much of this CT going to be exposed to the next state. So this is the basic idea of output get. Now we are going to understand another important concept of LSTM called cell state. That what is cell state here? If you see that this is the input to the previous state, and this is going to flow without much changing, or this change is a linear change. Now if ft is very close to 1, then this ct is very close to ct minus 1. Okay, now this is again true here. If ct, this is basically if ft is very close to 1, this ct minus 1 becomes ct, and so on. So there is a kind of information pathway that changes gradually through simple linear updates. And when you think of BPTT in this path, the gradient flows. So LSTM introduces a memory cell state and gets that regulate the flow of information. The core idea of LSTM is that the cell state CT, which changes gradually through the simple linear updates, allowing information to flow for long time step with minimal change. And that is one of the major advantage of LSTM to solve or to mitigate the vanishing gradient problem, giving this kind of uninterrupted or kind of very linear minimal change of this gradient flow or error gradient flow. Okay. Now the main question: how does LSTM solve the vanishing gradient? Now you see, instead of repeatedly multiplying hidden state, LSTM updates its cell state using the additive operation. That's what we have said. Ct is equal to ft into ct minus 1 plus it into ct. So new information added to the cell state rather than repeatedly multiplied. So there is less number of multiplication involved. Since information is added rather than repeatedly multiplied, gradients can flow backward with minimal decay. Now this is addition, not repeatedly multiplication. So from how C T is coming from C. This is multiplication. This mechanism called constant error carousel or seeds. As a result, gradients can propagate across many times without vanishing. That is the basic idea. Thus solve the vanishing gradient problem. So this is the cell state is the major aspect of the LSTM, which helps to solve the vanishing gradient problem. Next, how LSTM solves the long-term dependency issue. So what is long-term dependency issue? If the sentence like this: the movie which I watched last Saturday and absolutely loved was fantastic. Now this verb was depends on movie, not the loved. The simple alien may forget movie while an LSTM can remember through the memory cell, and that is very important. By virtue of this forget get, this input get, and this output get, we understood that this movie is to be remembered to be that with this word. So for when we are modeling this word, we are this what we are basically taking into consideration. Then this movie, because this long range dependency, it basically LSTM that kind of remembered this movie, what the normal CNN cannot, or normal RNN cannot, may forget. So how LSTM fix this? LSTM introduces the memory cell state and gates that regulate the flow of information. That we have seen in the last slides. The cell state acts as a memory highway, allowing the information and gradients to flow almost unchanged across the memory steps. This enables LSTM to learn long-term dependencies and greatly reduce the vanishing gradient. Okay, so this is the very important part. So here, this cell state is going to help LSTM to remember or to solve this long-term dependency issue. So that instead of repeatedly multiplying hidden state, cell state provide this equation f of t to c of t minus 1 plus it. If the forget get f is equal to 1, ct is equal to almost equals 50 minus 1. So this means the cell state, the gradient can pass through many time steps, little or no change, preserving long-term dependency and preventing the vanishing gradient problem. The movie which I watched last certainly, absolutely love, was fantastic. If it is f is equal to 1, we can remember movie, and this is associated movie, not with lot. So when f is equal to 1, so maintaining the previous state. So this is the way the problem has been solved. Long-term dependency problem has been solved. So in summary, in this lecture, we first try to understand what is the problem of RNA. The first problem, vanishing gradient, and it creates another problem, long-term contextual dependency. Then we introduce LSTM, we discuss the LSTM architecture, and then we try to understand how LSTM solves the vanishing gradient problem and thus the long-term contextual dependency issue. In the next lecture, we're going to discuss sequence modeling. Thank you very much.